Alright, so in this video we're going to take a look at the buck converter. Now the buck converter is a single class or a single topology in a class of converters called step-down converters. And basically what a step-down converter means is that the input voltage is larger than the output voltage. And so we can express that mathematically, let's say here. In general, we say Vn will be greater than Vo. And so here Vn is VDC and Vo is Vo. So what do we have here? We see two circuits, but they're really the same circuit. They're just two main ways of drawing the buck converter, and in case you see it one way or the other in the literature, you won't be confused. So you have some input DC source, VDC. You have a switch, Q, and again, this is drawn as a MOSFET, but it can be treated as an ideal switch. We imagine our switches are ideal for all intents and purposes, unless otherwise stated. We have an inductor, a capacitor, and then a resistor. So the important parameters we have here, we have IDC, IL, and IO. So the inductor current, the input current, and the output current. And same thing here again. And the voltages we're interested in are really this voltage Vx, which is the voltage between, or the node that connects the switch to a diode and the inductor here. The capacitor, we're assuming the capacitor is large. So let's make note of that. Let's say assume C is large. And so we can say that VO is DC. It will have some ripple on it in reality because this RC combination has some time constant. And what we're saying here is that it's large enough, or we've designed it to be large enough such that it filters out all the high frequency stuff, and VO is more or less constant. And again, as a result of that, IO should be more or less constant because this is a resistive load. Voltage and current are basically the same waveform. They would just be scaled proportionally depending on what the value of R is. So we have here what we call a switch mode circuit. And what that means is there's operating conditions here depending on the different modes of how this circuit operates. So what we have here is, and I think we forgot to mention or label this, really is what we can write here G, let's say, and we call G the gating pulse. Now every powered electronic converter has gating pulses, and gating pulses are how we control the switches. So when we apply a gating pulse, this will basically be a square wave like this. When we apply a gating pulse, when it's high, the switch will be on. When it's low, the switch will be turned off. And what we're going to do is we're going to use that fact to analyze this circuit. And what we're going to do is we're going to try to develop an expression for or a relationship between the input and the output voltage, because again the function of this is to basically scale down the voltage, let's say. So if you have some input voltage, let's say this is some rectified coming from the wall, you have let's say you have a transformer, a rectifier, and then you have this thing. Then you want to step down the voltage even further to a certain thing because you want to charge your phone or you want to charge your laptop or something. This VO would be set according to that charging requirement or that voltage requirement. So that's the kind of the situation we have here. So how do we analyze these circuits? The way to analyze the circuits is break it up based on switching, based on the switching periods. So basically in one case we'll have the switches on, in one case we'll have the switches off. So the objective here, or the goal here, is, let's say we want to plot, what do we want to plot? The main parameters. Let's plot G, we'll plot Vx, VL, VO, and IL. Analyzing these circuits based on waveforms and plots and subcircuits is probably the most, the simplest, I guess, is the way to analyze these circuits, because what you have are a number of different circuits based on a number of different switching conditions. And the easiest way to relate everything together is to really just figure out how the circuit behaves over one period and then go that way. We're also going to assume, so we will assume the switch is on for T on, and you have a switching period TS. So what I'm going to do then is I'm going to draw two subcircuits, and based on whether the switch is conducting or whether the switch is open, will have two different types of behavior. So let's imagine in this circuit that the switch is on. So we will draw here this diode as we had it before. We have this capacitor and then this inductor. So the thing we should understand first is how our parameters that we have that we're interested in. So we're interested in IDC, we're not really interested in IO, but I'll draw it there anyways. We're mainly interested in IL and VL. That'll tell us a lot in this circuit. We are obviously interested in VX and we are interested in VO. This is the circuit if G equals 1. We say Q is on. So when the gate of the device is fed a pulse, the device turns on and it acts as a short circuit. And I can add this here just for clarity. V across this thing equals 0. And in the other case, what we have is, let's say it's off. If the switch is off, we have a completely different circuit. Well, not completely different, but in functionality wise, we have a fairly different circuit, because now our input is no longer connected to our output, and the circuit kind of has to do its own thing depending on the elements that are present here. So we have this type of setup. And now in each case, what we're going to do is we're going to develop equations for VO, for VX. We want an expression for IL. We want an expression for IO. And then IDC. I don't think we're plotting IDC, but it's usually a good quantity to have as well. And now in this case, again, notice that V is not equal to 0. It's equal to VDC minus VX, which could be anything. You don't know what that is. And I forgot to label here the ground, and here the ground, and we can make the same note here that if G equals 0, Q is off. And we see that open circuit, it must be off. So we still have here VL. And again, what we're interested in are these parameters. So let's take a look at the circuit on the left first. So in the circuit on the left, what are we interested in? We want G, we have G. G equals 1. What else do we want? We want Vx. What does Vx equal? Vx is exactly equal to VDC, because this is short. Now what's happening with this diode? This diode is reverse biased, because VDC is a voltage, positive voltage, we assume. If this is a positive voltage and this is the diode is connected directly like this, it would be reverse bias diode. And Vx is basically the exact same thing as VDC. So we say, and I should write this with a capital because this is a DC voltage, and we usually use that. In the literature usually uses that as well. So Vx equals VDC. What else do we need? We need VL. VL is the voltage drop across the inductor. So we have Vx minus VO. So you have Vx minus VO. And again, I could use a VO, capital VO here, I guess, technically more correct, because we're assuming that voltage is basically DC. So VL is Vx minus VO, which is, we know that is VDC minus VO, because Vx we just found to be VDC in this case. What else do we have? We want to find IL. IL. Now what's IL? IL, and here's I guess this is a bit of a side note. So if you have an inductor, and the inductor is fed a voltage, we know that VL equals L dIL by dt. Okay? That means the inductor current is 1 over L times the integral of the applied voltage. Now, if this applied voltage is a square wave, which is what we kind of have in this case, not kind of, we absolutely do, that means the integral of this voltage should be a ramp, meaning this current should increase rampwise and decrease Well, the actual value of where it'll go up to depends on the inductance and the initial conditions. But the point of the story is, as you apply a positive voltage, the current in the inductor increases rampwise. And as you apply a 0 or a negative voltage, it'll start to decrease rampwise. Now, what's the slope of this? The slope of this, you can prove this. The slope of this, let's go to the rise, I guess. It'd be more useful to take this. It'll be VL over L. And so VL in this case is what? It's VDC minus VO. So we see that this should be VDC. Well, it should be capital. VDC minus VO divided by L. But this is a time varying function because it'll increase, and it's only true like that up to this point. So let's call this T. So this is your slope, and this is the equation of a line. I'll get rid of this stuff now because we don't really need it anymore. So these are the equations that I think we're missing one. We had 5 parameters, right? VO. Well, VO is going to be a DC value, so we don't really need to know. Let's just say that VO equals VO, and we'll assume it's some constant value because there's no, you're usually given these type of things, this parameter of what it should be for a design. In this case, we're just talking about the general theory. So what happens in this case? You have here G equals 0. You have Vx equals what? Here's the sort of physical explanation as to what's happening here. So in this case, imagine when G equals 1, you have this current IDC. This diode is basically turned off. So maybe we can just get rid of it entirely. So the diode's gone. And now this current goes through the inductor. Now we know that inductor currents can't change instantaneously. So as soon as you turn the switch off, this current has to come from somewhere. It can't just disappear. So what happens is it forces the diode to turn on. And as it forces the diode to turn on, this current IL starts to flow like this. Because the current has to come from somewhere. It can't just be shut off that way. That's not how inductors work. So it'll force the diode to turn on, and it'll draw the current from ground. Or the ground node, whatever you want to call it. So Vx in this case, this we can replace, let's replace this with a short because the diode is on. And maybe we can just get rid of the diode altogether and say that that's a short because the diode is on. And what you end up with is Vx equals 0 because it's shorted to ground. Vx equals 0. What's the next thing we want? We want VL. VL is equal to, again, it's equal to Vx minus VO. But Vx is equal to 0, so it's just equal to minus VO. And then we want to find IL, and IL is equal to VL over L times T, which is equal to negative VO divided by L times T. And again, VO equals VO, which is what we know from before. So now what we're going to do is we're going to plot this, and then after we plot it, we want to take a look at something we call the conversion ratios, which is a very important quantity in any converter that you have. So we have here a axis or plot, I guess you can say, multi-axis plot, and I want to plot all of the interesting quantities that we have, or the quantities of interest, let's say. And so one thing I probably should do is add breakpoints here so that we can understand what it is exactly that we're looking at per period, and it'll simplify things, I guess, for us, especially in terms of, I mean, there's a bunch of things going on here. So what do we want to do here? I'll plot this for like a period and a half, and then it's just repeating. So we say this is T on, we say this is TS, and we say this is TS plus T on. So this is one period, 0 to TS. And these are all time, of course. And the parameters that we're plotting is, it's usually a good idea to plot G first, because that's kind of what's controlling the behavior. Here we'll plot Vx and VO. Here we will plot VL. And here we'll plot IL. So G varies between 0 and 1. Let's imagine it starts off being 1. Okay, so it's 1 here, and then it drops down as soon as we say it's off, because remember, we said that the switch should be on from 0 to T on. Then it stays off for this period of time, and then it turns on again, and then it turns off at TS plus T on, and this behavior continues indefinitely unless something changes. Okay, we said that VO is some constant value, so let's imagine it's some constant value. I don't know what it is. Let's imagine that this dotted green line is VO, okay? We don't know what it is. We don't really care what it is. We just know that it is some value. That is basically a DC value. Vx, what is Vx doing? So let's go back up to our equations. We see that when Vx equals, or when G equals 1, Vx equals VDC. And then when G equals 0, Vx equals 0. So Vx equals VDC when G equals 1. So if G equals 1, Vx equals VDC. And when it's not 1, this equals 0. So this is the waveform that we see here. So it's varying between 0 and VDC. And that'll carry on. And so I should probably make note here that this is Vx. And so we were right to not give this a DC. So this is a lowercase, which is correct, which is what we expect. Now, what about VL? So let's take a look at VL. VL, if we go up here, we see VL when G equals 1, VL equals VDC minus VO. And when G equals 0, VL equals minus VO. So this is, again, it's going to be a square wave, some type of square wave. It's not really going to be square, but it's going to be a rectangular wave. And the amplitude isn't, it's not going to be symmetric, I guess is what is the thing we should understand. Because we know that VDC is greater than VO. VDC minus VO is the positive end, and then it's going to go to minus VO. So we know that since VDC is greater than VO, there will be some asymmetry in this case, in the actual waveform. So if I draw the actual waveform, what you would see is that this will vary between, and I don't want to cut too much into the IL waveform, I guess, so maybe we can go here. Let's say it varies between this point, and then it goes down, and let's say it goes something like this. I think I've gone too far down, but that's all right. We can move the other one down if anything. So it goes between these two values, and I'll label these values in a second. But as I said earlier, drawing these waveforms has a lot to do with breaking things up into subcycles, I guess, is the way I would put it. So this voltage here is VDC minus VO, and this voltage here is minus VO. So it varies between these two values. And then the inductor current, and again, we're assuming that this converter has been running for a while. Otherwise, it would start from 0, obviously. But we're assuming that it's been running for some time, and so it's a non-zero current. So let's imagine that it starts here, and it increases ramp-wise. Maybe we can use a different color because it's kind of, or it's not even kind of, it's very close to that. So let's use this blue. So it increases like this, ramp-wise, and then it decreases because you're applying a negative voltage to it. So now you expect it to go down. And then it'll increase here to roughly the same part, and then it'll decrease here. And now what's the slope here? We calculated the slope, or we derived an expression for it at least. We said it was VDC minus VO divided by L, and the slope here is negative VO over L. And negative VO is a negative number, therefore we expect the slope to be going down. So that's what we have here. Now, something important to note here is that we call this mode of operation, we call it continuous conduction mode, often abbreviated as CCM. What this means is this inductor current never reaches 0. So in this mode, we say IL is always greater than 0. This current will never touch 0. And that's how we quantify continuous conduction mode, because as soon as this touches 0 or goes below 0, we start to see some strange behavior. And we'll look at that in another video. But the analysis of that kind of a circuit is a little bit more involved than what we've seen here. So we're almost done with this analysis, but we want to do one more thing, and we want to determine what is called the conversion ratio. So the conversion ratio relates the input, not ration, relates the input to the output. So we want to know, how are the input and the output related? How can we control the input and the output? So let's define something. Let's define what we call the duty ratio. And we call this duty ratio D as being T on divided by TS. So the fraction of how long the switch is on versus how long the period is. If this is the definition that we have, what we're going to do then is we're going to apply our volt-second balance. And if you haven't seen the video on the introduction to power electronics, there's a link down in the description for you, so you can take a look at how to actually look at, or how to apply the volt-second balance, or what the volt-second balance actually is, if you're not familiar with what it actually is. So here we can say apply, I'll say VSB. If I apply the volt-second balance, we say that the volt-second balance is from 0 to TS, VL of T dt should equal 0. Okay, so let's go up for a second and let's take a look at what we have. VL for the first part, so from 0 to T on, it's VDC minus VO. And then from T on to TS, it's negative VO. So we have to keep those things in mind, because we're going to basically break this circuit up, or this equation, the integral up, into two parts. And we're going to evaluate it basically. So we say from 0, and I guess one thing we should do before we do that is we should say that T on is equal to dTs. Just rearranging that, because here what we're going to do is we're going to write everything in terms of TS, and we'll see we can divide everything out after. So 0 to, let's say, dTs of VL. We said that between that period it was VDC minus VO, capital VDC minus VO dt. And after that we said that from dTs to TS, this is equal to minus VO dt, and that should equal 0. So when you evaluate this integral, you should see that this is VDC minus VO dTs plus minus VO times 1 minus dTs equals 0. So the first thing you can do is get rid of these. And if you rearrange this and solve this, what you'll find is that VO is equal to dVDC. This is a very important relationship, because what this is telling us is that the output voltage can be controlled directly by controlling D. Now what is D? D is the fraction of how long the switch stays on per switching period. So if you go up here, and if we play with this, so for instance, if we play with this on time, let's say for a second that we made a new switching pulse, and this switching pulse did something like this. This dotted yellow, purple line. We would expect that in this case, so this, let's call this T on prime. So T on prime is clearly greater than T on, which means that VO, let's say VO prime, would be greater than VO. So you can adjust the output voltage based on this pulse. And this pulse would be generated by some microcontroller, or some, you can even have, let's say, something like a 555 timer if you want to go analog. But the point of the story here is that this duration here of how long this pulse is on dictates how the output voltage is related to the input voltage. And this is the most fundamental relationship you'll see between converters, I would say, where the output is related to the input just by a factor of D. And D is always between, I guess we can add that as well. Since T on is always less than TS, we can say that D is always between 0 and 1. So it can't be greater than 0. It's a fraction, so it can't be less than 0 and it can't be greater than 1. And if it, I mean, in the best case, it would approach 1, but then you would see very strange behavior in your parameters and your circuit elements, and things might go a little crazy. So we mentioned here again that this is for continuous conduction mode. You'll see that in the next video that the discontinuous conduction mode, the relationship is not so straightforward, and the whole analysis is a little bit more involved. So that's it for this video. We looked at the buck converter. We looked at how to analyze switch mode circuits, break them up into 2 different circuits, and then analyze all of the parameters we need. Plotting waveforms is always a useful technique. It shows us all of the different behaviors of the different things that we're interested in, all like side by side next to each other. So we can see, for instance, that VL is a positive square wave here, so we see that this should be increasing. We see it's a negative square wave here, so this be decreasing. And so these kind of relationships are very useful when we're analyzing this type of circuit. And in this case, maybe it was a little bit simple, but you'll see as we do more and more advanced circuit topologies that this method of analysis is very useful. So I hope you found this helpful. If you haven't already, hit that subscribe button so you get notifications whenever we have new videos available for you. If you have any questions, feel free to leave them in the comments. I will link some other additional power electronics related videos here that may be useful, especially the introductory one. If you're not familiar with the volt-second balance and the capacitor charge balance, taking a look at that video is very useful. Thank you guys for watching. I hope it was helpful, and we'll see you in the next one.